Hi, my name is Ashley Maloney, and today I will be talking about multi-technique Auger electron spectroscopy, and specifically I'll talk about the complementary nature of Auger, FIB, EDS, and EBSD, all available in situ on our 710 instrument. As many of you know, there are multiple different types of information that's possible to obtain with Auger electron spectroscopy. The first type of information is secondary electron imaging, which can provide high magnification visualization of the sample. Another type of information we can get from Auger is quantitative elemental and chemical spectral analysis. So we can determine what elements are present as well as their quantity. And in some cases, we can determine the chemical state of elements in some materials. The third type of information we can get from Auger is elemental and chemical imaging. So we can get two-dimensional elemental distributions and in some cases chemical state distribution information for some materials. And finally, we can conduct sputter depth profiling to reveal the thin film and interfacial composition. AES is an analytical technique that provides compositional information from just the top few monolayers of a material. You can see in the diagram here, if we have a primary electron beam that interacts with the sample surface, it creates a large volume of interaction, and this large teardrop shape is where we get characteristic X-rays for EDS analysis, for example. But if you look at the top of the teardrop, that's actually where our Auger electrons are coming from, and you can see this creates a very small spot size as well as high surface sensitivity. In AES, we can detect all elements above helium in the spectrum. Typical detection limits are about 0.1 to 1 atomic percent. We are very surface sensitive, so our Auger electrons are coming from about the top 5 to 75 angstroms of a sample surface, and we can get very good spatial resolution down to about 60 angstroms probe size. In our 710 instrument, we have multi-technique options available. One of the techniques is energy dispersive spectroscopy, EDS. We also have backscatter electron detector, electron backscatter diffraction, focused ion beam. We have a cold fracture and parking stage, for contact heating, and we also have a 25 millimeter and 60 millimeter transfer vessel so that you can transfer samples from system to system without breaking vacuum. If we take a look inside the enclosure, this is what you'll see. So this is our main chamber. And you can see on the left we have our CMA column. This is our ion gun source, our 5-axis stage. This is a port where the FIB would go. This particular photo on the left doesn't have a FIB installed. This is the FIB port. We have our EBSD detector, SED, EDS. And then if you look in the middle picture, this is a picture of a system that does have the FIB, and this is what the FIB looks like on the system. And if you take a look inside the main chamber, you can see all of the different sources and detectors and the geometry of those related to the sample surface. Here's a quick summary table comparing Auger electron spectroscopy to EDS and EBSD. Of course, each technique has its own pros and cons. Auger, for example, has a much better spatial resolution compared to EDS and EBSD. It does have a shallower sampling depth, but this can be useful in some cases to have EDS available on the system as well when you want information from deeper beneath the sample surface. And that's what we'll talk about in the next few slides. This is an example of a titanium passivated aluminum surface. And we can see here, we start out with EDS analysis. And the reason we do this is because EDS takes very fast maps. So we can quickly locate regions of interest on our sample surface and get spectrum in a timely manner. So here we have the SEM image and the corresponding EDS spectrum from the SEM image. And if we look at the EDS maps that are collected from this field of view, we see distributions of magnesium, carbon, and oxygen and aluminum that are consistent with the rolling pattern of our aluminum surface. However, we do see silicon and iron that are in these kind of isolated regions that don't match the rolling pattern of the aluminum and are of particular interest because these are elements that we would not expect to see in this aluminum sample. So if we zoom in on one of these features of interest, and again, we're still with EDS here. If we zoom in here in our SEM image, we can kind of see this feature in the SEM image. Again, the carbon, oxygen, magnesium, and aluminum are pretty much in congruency with the rolling direction of the aluminum. However, we have the silicon and iron that show up as hotspots. So the idea here is we want to switch over to Auger in order to collect high spatial resolution images of these defect areas. So we switch over to Auger, and again, here's our EDS spectrum we collected from the same region in our SEM image. If we look at the Auger spectrum, we see carbon, titanium, oxygen, fluorine, magnesium, and aluminum. And those are all detected in the EDS spectrum as well, and we saw them in the EDS maps. So it's not a huge surprise to us. What is rather surprising is the absence of iron and silicon that we are clearly seeing in the EDS spectrum, but are mysteriously absent from the Auger spectrum. If we look at the Auger maps, then we can see again the elements that are present in EDS. We see them in a distribution that are consistent with the rolling pattern of the aluminum preparation, but we don't see the iron and silicon that we were seeing as very bright and very apparent hotspots in EDS are just not appearing anywhere in the Auger spectrum. So what we then did was we took a FIB cut through the particle that we were seeing in the SEM image. So this is the FIB cut in the freshly exposed FIB face. If we then zoom in on this feature, we can see that there's this platelet shape of the defect that's present in the SEM image. And then we conducted an Auger map of our freshly exposed FIB face. And interestingly, we can see this layer of iron that's just below the sample surface and is actually platelet shaped. This is very interesting because it really shows that we needed EDS in order to detect this feature in the first place. Without EDS, our Auger analysis from the top surface wouldn't have detected this iron present at all because it is buried below the surface. However, we also needed FIB in order to expose this buried feature, as well as AES to map the feature with high spatial resolution and to show that it is actually platelet shaped. It's not obvious from the EDS maps that this defect has this particular geometry. Therefore, we needed the FIB cut and the Auger mapping in order to see that it is a pretty flat defect. Again, this is all done in situ without breaking vacuum. So we have the advantage of being able to quickly do our EDS maps and then also do the FIB cut and Auger maps while keeping the surface pristine. In this last example, I would like to show the complementary nature of Auger, EDS, and EBSD. And this is on a carbon steel sample. In this carbon steel sample in the SEM image, we were seeing some of these darker areas in the SEM, and we wanted to chemically characterize those features. In Auger, we see the sulfur distribution is spread out a little bit more than it is in the EDS map. And this actually corresponds to this dark area we're seeing in the SEM image. So we're seeing that the sulfur has a different distribution near the surface than it does deeper down in the bulk of the material. We can also get EBSD information for the grain boundaries and strain fields, and this can help us predict where localized corrosion is likely to take place when the surface is exposed to a corrosive environment. In conclusion, I hope I've shown you today that we can use the multi-technique scanning Auger nanoprobe as a complete compositional analysis for many applications, including nanotechnology, semiconductors, advanced metallurgy, advanced materials, and many other types of applications. Thank you, and I'll be happy to take any questions.